a geometric sequence, which can look quite confusing to look at. It's a whole bunch of new variables that we've never really talked about, but that's fine. Our t to subscript, that's what's usually known as subscript n, is the term value, okay? Or a is the first term in the geometric sequence. The r is the ratio that it's growing or decreasing in size by. And the n is the term number, okay? And it's the n to the power, it's r to the power of n minus 1 in your formula. If you're ever trying to find, and I've written this out here, but usually it's actually written, if you want to find the common ratio, you can just take, your original term and divide it by the term that comes before it, or you can take the term that comes after it, so they say plus 1, and divide it by the original term. Both of these are kind of saying the same thing, it just depends which terms you have. Okay, and that's a way to find common ratio in case you don't have it. So in our first example, for example, they gave us some values, 3, 12, 48, and 192. Quickly, you can probably look at this and deduce that it's growing, probably multiplication, and I know my multiplication table is relatively well, so this is times 4, and I test it out again, works out really nice. But say I wanted, there were values I was familiar with, so I need to find the common ratio. I can use this formula. We would call this your T1, okay, and which make this T2, T3. So according to this formula, R is equal to our first term and divided by the term before it, or the term after it divided by that. So we can say we started with this one, our T4, okay? We took T4, and we're going to divide by the term before it. So 192 divide 48, okay? And that gives us a common ratio. And it should be 4, but we'll prove it here by using the almighty calculator. It ends up as 4. So great, we know our common ratio is 4. Because they gave us the sequence, we know our A value is the very first term. So that's going to be our A value in this when we go to build our formula. Okay, what did they even ask us? They want us to find T10. I really should have wrote out the rest of the question here. Okay, so please find T10. Well, we could obviously continue this ratio, or we can use our formula. So let's build the formula we have. Okay, so the term value is equal to the original first term. So this is our A. Yep. Excuse me. Our common ratio is the value 4. Great. So this is our R. So 3 times 4, and to the power of n minus 1. Okay. The n here is 10. That's what they're looking for. They want our n term. So our term value is equal to 3 times 4 to the power of 10 minus 1, which is 4 to the power of 9. Okay, so 3 times 4 to the power of 9, which will give us a term value of 4 to the power of 9, and then times 3, huge value, 786,000. So 786, and then what were the other 3 terms? 432. Okay, 432. Great. So we've used it. Kind of looks decent. But really what this is, and you've actually worked with this, is you've worked with exponential functions. Exponential functions are usually written in the form of y is equal to a times b, okay, to the power of x. Well, they use the exact same first letter. The first term is a. That's what an exponential function is. It's the very first term. B is technically the r in what they've done. Okay, the term value is our n. They use a also. And the only real difference here is we use n subtract 1. And there's actually a good reason for this, n subtract 1. And the reason is the very first term we talk about is T1. Usually in a geometric sequence. But with an exponential function, usually the first term or the x value can start at a value of 0. So let's show you this kind of idea on a graph. We had 3, 4. We'll use the example of the equation we found. Okay, here's their formula. Okay, and we'll use the same thing. Y is equal to a. It's the exact same a times b to the power of x. I need a slider for b. So I'm going to keep the ratios the same. So I'm going to change this number to 2. We have our 2. Our a value is 1. And this one has x minus 1 in there. So, okay. Now, we could have done the same thing and put this to the power of x minus 1. And now they overlap. They're technically the same. But they have minus 1. And the reason being here is because they start at the value of 1. Our first term is 1. Yeah. So your first term, your a value, is what we started with. Our question, what did we start with? A was 3, right? A was 3, and
R was 4.
R was 4. Great. So let's change these to those same common ideas. They're overlapping. They're doing the same here. But you see, our y-intercept isn't the value of 4 in this case. What that is when x is equal to 1, that's our first term. Okay. So geometric sequences are exactly exponential functions, except when we talk about exponential function, we usually refer to a y-intercept. But in a geometric series, we refer to when x is 1 as the very first term. So that's why they have to put this little subtract 1 on top of the equation. It really is the exact same thing. For instance, if I didn't have exact 1, I still have an exponential function here, okay? And it's just been shifted to the right, okay? My y-intercept is 3. Have you done translations of exponentials?
No.
Not really? Okay, but it's the same function, just moved to the right, 1 unit. Okay? So if you're familiar with exponentials, it can make building a geometric sequence much, much simpler to do. It's really just building an exponential function because it's increasing by some ratio. And that's what exponential functions really are. Okay?